Hi. In previous lectures, we've talked about culture as being many coordination games. What I want to do in this lecture is introduce yet another model of culture that's based on those coordination games that brings in some other features. Now, this model was developed by Jenna Bednar, who's a professor of political science at the University of Michigan, along with me and two of our graduate students, Aaron Bramson and Andrea Jones-Roy. What this model tries to do is include two things that were missing from the previous models. What are those two things? Well, the first one is this notion of coherence and consistency. Remember Trilling's definition of what culture is. Remember he talked about making a coherent life. Well, that coherence can be seen. Remember, if we look at the data from Ron Englehart's World Values Survey, we see there's a lot of consistency across countries. So we see Protestant Europe looks the same, Catholic Europe looks the same, the Islamic countries look the same. And what that means is there's a consistency to behavior. So if you're in Sweden, let's say, and you see how people behave in one context, you can predict pretty well how they're going to behave in another context. It's that consistency we want to try and understand. There's something else we'd like to try and understand, and that is the tremendous heterogeneity within cultures. So remember when we looked at Sweden, it wasn't everybody was at one spot. There was a giant scattershot of behaviors. There was our there is no great blue heron idea. And the same was true when we looked at Zimbabwe. Zimbabwe wasn't just one point in the lower left-hand corner. It was a whole spread. So what we'd like is we'd like a model that gives us the consistency. So why is Sweden way up here and Zimbabwe way down here? And we'd also like a model that gives us some sort of heterogeneity within culture. Well, here's the funny thing about models. That's sort of an easy thing to do because all you have to do is make assumptions so that you get those results. So for example, all we have to do to get consistency is to say, let's let the values that people coordinate on, the actions, the behaviors, beliefs, whatever they are, have some meaning. And let's assume that people desire some consistency. So then what we'll probably get is if people have preferences for consistency, we should get some consistency. Let's also throw in just a tiny little bit of innovation. And what we can do is we can ask, okay, how much innovation or errors do we have to have in people trying to copy other people or coordinate with other people and trying to be consistent to get the sort of variation you see in those pictures, right? Because when we look at these pictures, we see massive variation. So that would suggest what we probably have to have is substantial rates of innovation or errors in order to generate that. So what we want the model for is to explain how does this work? Do we have to have a lot of innovation errors or just a little bit? And how much consistency do we need in order to get consistency in the model? So here's what we're going to do. We're just going to change the model by assuming one extra thing. We're going to assume in addition to people trying to coordinate, we're going to assume they also try and be consistent. And I'll explain what that means in a second. And then we'll also just throw in these tiny errors. So remember our coordination rule. How does that work? There's two people, they meet. They've each got these vector of actions or beliefs or attitudes, whatever you want to call them. And when the leader and follower meet, they look at this second dimension. Let's say the follower says, well, you're a 3, I'm a 1. I'll switch that to a 3. That's what coordination is. You switch your action. You put the ketchup where your friends put the ketchup. What would consistency be? Well, consistency would just be this. You look at yourself. Now these values 5, 3, 1, 4 have meaning. 5 is close to 5, 4 is close to 4. And you look and you think, I'm 5 on the first, I'm 1 on the second. And that doesn't make any sense, so you switch and become 5 on both. What would that be? Let me give you an example. So suppose that you are from a family that's pretty reserved, and so you don't even hug your parents very often. And then you go to college, and all your friends are hugging each other. So now you've got hugging behavior 5 with your friends. Well, then you go home and you realize you're hugging someone you just met a month ago to say goodbye, and you're not even hugging your own mother. And so you've taken this action 1, which is not hugging. So what happens is then you switch, and you say, you know what, if I'm hugging my friends, I might as well hug my mother. And you become 5, 5, and you change your behavior to become more consistent in terms of how you behave. So those are the two rules. We're going to assume that people try and coordinate with other people, and they want to try and be consistent. So what should happen? What you'd expect to get is you'd expect to get consistent, coordinated behavior. You'd expect the system to just, boom, run right in. Well, here's what's funny. So when we ran this model, when Jen and I and Aaron and Andrew ran this model, this happened, but it took a long, long time. The process took an incredibly long time to converge. And the other thing is when we threw in tiny errors, when we threw in just little tiny errors, not big errors, then we got those big clouds like we saw in the picture. So when you see those clouds, like of all the spread in Sweden, all the spread in Zimbabwe, you might think, well, a lot of people have to be innovating or trying new things or making errors. Instead, it turns out only a small number of people have to get that level of heterogeneity within the community. So that was a surprising result. By constructing the model, we saw that tiny, tiny amounts of error innovation lead to these big spreads. Now the question is why? What's causing that? What's giving us this giant spread like this with just tiny amounts of errors? Well, here's where we have to think through the model. So let's suppose our model converge to everybody being 5 on everything. Now let's suppose somebody decides to innovate a little bit, and so they change to 6 on this thing. So they just try something new. We might think that should go away because if they try and be consistent with themselves, then maybe they'll turn that into a 5, or if they meet somebody else, they'll turn it into a 5. But there's another possibility, and that is when they meet somebody else could copy the 6. And there's a third possibility, which is they themselves can move something else to a 6 if this 6 works. So what you get is that 6 can spread this way, can spread sort of, you can think of it as vertically across society. It can also spread horizontally. So it could also spread within the person. So you've got these two directions it can go. It can go horizontally within a person, and it can go vertically across people. What this means is that these innovations or these mistakes can spread in two directions, which means the process isn't going to converge very fast, and it's going to mean that you're going to get a lot of spread because errors are going to propagate in multiple directions. So you have someone make a mistake or innovate here, and it spreads both within the person and across people. And then if another error happens here, that could spread within the person and across people. And then you've got all this heterogeneity spreading out. Now at the same time, though, the system is going to maintain substantial levels of consistency. Most of the things are going to be 5s, but there's going to be 6s and 7s everywhere. So this is just a picture of it. What you'd like to do is understand, can we understand this at a deeper level? Can we mathematically understand why small amounts of error or innovation are causing this big spread? We got a picture of it, but it'd be nice to nail that down. Well, here's how we nail it down. We construct an even simpler model. So sometimes when you want to understand a process, what you do is construct an incredibly simple model. So here's what we're going to do. We're going to construct a model with 2 agents, 2 games, and 2 actions. So people are deciding whether to hug or bow with their family and hug or bow with their friends. That's it. So now we can write down all possible states of the world. So let's think of it this way. Here's game 1, and here's game 2. So we'll call them the column 1 game, column 2 game. Here's person 1, and here's person 2. So what you have is it could be that both of them are doing the same thing on both games, so the system would be coordinated and consistent. It could also be the case that one of them, the person 2, is taking the red action on both games, but person 1 is taking the green action on game 2, so we could call this off by 1. So there's one person changes that one thing, then everything would be coordinated and consistent. Now another thing we could have is we could have that the people could be consistent but not coordinated. So person 1 is green on both things, and person 2 is red on both. Finally, next, they could be coordinated but not consistent, so they could both play the red action on game 1 and the green action on game 2, but they'd have a lot of cognitive dissonance because neither one is consistent. And then finally, it could be a total mess. Neither person could be consistent, and the 2 couldn't be coordinated. Let's first look at this system without any error, with no noise terms. What do we get? Well, here's what the dynamics would look like. And let's just look at the consistency dynamic first. If we're in this state where people are off by 1, one thing that could happen is this person, person 2, could look at themselves and say, am I consistent? And they would say, yes, I am consistent, and nothing would change. Alternatively, person 1 could look at herself, and she could say, am I consistent? She could say, oh my goodness, I'm not, and she could switch. Now there's 2 possibilities. One thing she could do is she could switch and have them both become red, and then what would happen is both people would be consistent, but neither would be coordinated. Or alternatively, she could look at herself here and say, oh, maybe I'll make them both green, and then the whole situation would be coordinated and consistent. So each of these would happen with probability of half. That's the consistency dynamic. We could also write down the coordination dynamic, and we can do it for all of these different states. Here's what this is going to look like. It's going to look like a map where we write down all the different states, and we can write down the probability of moving from those states to other states. So let's just do a couple cases. Suppose we're here. This is the case that's a total mess. Well, if someone looks at themselves and decides to become consistent, then let's suppose it's this person on the bottom, person 2. If they become consistent, then we'll move into the off by 1 state. Or alternatively, suppose that 2 people meet and they decide to coordinate. Well, then again, we'll move into the off by 1 state. So no matter what happens with probability 1, we're going to move from this state, the total mess state, into the off by 1 state. Now, once we're in the off by 1 state, a whole bunch of stuff could happen. One thing that could happen is that we could stay in the off by 1 state. How could that happen? Well, that could happen if this person looked at himself and decided to be consistent, or if these two people, if the people in game one decided to coordinate, because nothing would happen, you'd stay in the state. Alternatively, it would be possible to move over here to this side to the right where both people are consistent, but they're no longer coordinated. Alternatively, it would be possible to move down here where they're each coordinated, but they're not consistent. And you could even move over to this state, which is the coordinated consistent state. And this is the only one that's stable, because if you're here, you're not going to move out. Now, when you look at this, this is a complicated map. But you look at this, you think, wow, this reminds me of something. And it should remind you of a Markov process. However, it differs from a Markov process in that a Markov process, one of our assumptions was you can get from any state to any other state. But that's not true of this state, this equilibrium state right here. Once you're there, you're stuck there. But remember in our model, though, this here I'm assuming there's no innovation. Remember in our model, there's a slight chance of innovation or making an error, some epsilon. And if you make it an innovation error, you're going to move to the off by one state. So that would put an arrow back in this other direction. And now we have a Markov process. So the way that Jenna and Andrea and Aaron and I captured this process, and the way we tried to model it, was to say, okay, here's all these states, and now we've got a Markov process. And once you've got a Markov process, guess what? We just write a big matrix. We just write down all of our states. Here's our states at time t, and here's our states at time t plus 1. And we say, what are the odds that you move from one state to the other? And you just write a giant matrix with all those numbers in it. And then you can analyze the matrix and figure out how much of a spread you get. And what you get when you run that is you get that small innovation rates, really small innovation rates, lead to substantial heterogeneity. So our model gave us a big surprise. So what do we have total then? When we think about cultures, what we see is we see differences between them. So people from France behave differently than people from Mexico. We also see similarities within, and that's what we got in this last model. We see that the people within within an interacting group become similar. But notice how we say similarities within, not identical behavior within. There's a big spread, a lot of within group heterogeneity within Sweden, within Zimbabwe, within Greece, within Spain. And finally, some of that behavior is interesting in the sense that it doesn't appear to be optimal from outside. Now, if we go back to our model, if we go back to this model of our Markov process and our consistent behavior, one way we can get the interesting behavior is that it could be that maybe if I'm doing 5 on each of these things, that this 5 isn't optimal. It's not the right thing to do. However, we're choosing to do 5 because of the fact it's consistent with the other things that we do. What we've learned here is that we can explain something like culture, not all of culture, but we can at least get some insights into culture by thinking of it as coordination, by thinking of cultural behavior as coordination on a whole range of activities. And if we're trying to coordinate with other people, that can explain why people from different cultures are different, just because we've managed to coordinate in different ways. There are 3 ways we can coordinate on the wrong action. First, we could just idiosyncratically coordinate on the wrong thing. Second, remember in the shaker bow example, we could have had it be the case that payoffs changed over time, and shaking was better originally, but bowing is better later. And then third, as we just saw, it could be in order to maintain consistency, we could choose a behavior that's suboptimal in one domain because it makes us consistent with our behavior in other domains. So what we've thought of here is we've thought of culture as multiple coordination games where what we're trying to do is be consistent. And that makes a lot of sense, is what we're really trying to do in order to make a coherent life is to have somewhat consistent behavior across a variety of domains. And also, in order to get good outcomes, it's important that we put the ketchup in the same place, greet people the same way. So we have to coordinate with people around us. So these very simple models have explained differences within culture, similarities across, and why we see interesting stuff. And the one surprise we got in this last model is that, when we actually look at the data, we see, even though people are trying to coordinate and be consistent, we see a big blob. We see a lot of within-group heterogeneity. We could explain that with our model by saying, that happens even if there's just a small amount of error experimentation because of the fact that errors propagate in 2 directions. And that was the intuition we had, and we could put that in a Markov model. And by analyzing the Markov model, we can see, in fact, that was the case, that small errors do, in fact, propagate. And the equilibrium of that Markov model for even small epsilon has large levels of heterogeneity. So we can explain those large levels of heterogeneity, or at least why a process like this might produce them from the dynamics by using the Markov model. And that's sort of the last point here, is that when we look at these coordination games, It was easy to write down the model, like there's a bunch of people and they coordinate. But then what do? What we could do, which was great, is first off, we could use our Lyapunov model to show that pure coordinating behavior creates a Lyapunov function, so the process is going to very quickly converge. It's people trying to coordinate should very quickly converge. Then when we threw in the error terms and we threw in consistency as well, we now no longer had a Lyapunov function, but we could use our Markov model and explain why the system ended up going to an equilibrium with a lot of heterogeneity. So one of the reasons why we want to construct a bunch of models and learn a bunch of models is we can use them sometimes to analyze other models. And that's what we did here. So we used our Lyapunov model and our Markov model to analyze our culture models. If we didn't have those skills, if we didn't have the Lyapunov model and the Markov model, we couldn't have done much with the culture model. We just could have written it down and said, well, this sort of explains some things, but we don't know what happens. But because we had those other two models, we can analyze in full what does happen. So this concludes our discussion of culture. It's a constrained discussion. There's a lot more to culture than this. And that's why there's hundreds and hundreds of definitions. And we need hundreds of definitions because culture is a complex thing. But what these simple models have allowed us to do is understand some basic properties of cultures, which are that there's a lot of differences between cultures. And those differences may arise because of the fact that people need to coordinate within groups with which they interact. There's also consistency within cultures. And that happens because it's just cognitively easier to do the same behavior in lots of different domains. And then third, we see a lot of heterogeneity within cultures. And that happens, as we saw by using a Markov analysis on our model, because if people just make small mistakes or occasionally try an innovation, those differences are going to propagate through the population in two ways, within an individual and across individuals. And that's going to give us a lot of within culture heterogeneity. So cultures differ between themselves, cultures differ within themselves, but they still have this consistency. They have what you might call a cultural signature. These very simple models, combined with our tools of Lyapunov functions and Markov processes, have helped us understand why that happens. All right, thank you.